Alright, let's take a look at equations of motion in rectangular coordinates, and you might see equations of motion written as EOM. So refer to equations of motion. Okay, so we're looking at when a particle moves relative to an inertial XYZ reference frame. The forces acting on the particle as well as its acceleration will be determined in terms of I, J, and K components. So if let me go ahead and make a coordinate system real quick. And let's say we have some path. There's some particle on the path. We can describe its position like so. And it would have some y coordinate, some x coordinate, and some z height. Okay, now we'll also possibly have forces in these directions. So we could have, it's not straight, a force in the z direction. We could have forces in the y direction. And we could have forces in the x direction. And this would be just for rectangular coordinates. We're going to look at different coordinate systems in the future, but right now the majority of the problems can be solved in rectangular, and in that case we would say the summation of the forces is equal to mass times acceleration, and then we break it up like this. We'd say the summation of the forces in the x direction times I plus all the forces in the y direction times the j component plus all the forces in the z direction times the k hat component is all going to be equal to the scalar mass times the acceleration in the x plus the acceleration in the y plus the acceleration in the z direction. In most of our cases, we're probably not going to be using the z direction, but let's derive everything like we need to. That's really the majority of this chapter. All I do is go ahead and say that you can break these all into components now, where the summation of the forces in the x direction is equal to the mass times the acceleration of the x. The summation of the forces in the y equals mass times the acceleration in the y. And the summation of the forces in the z direction, every time, in the z direction is equal to mass times acceleration in the z. Alright, this is rectangular coordinates. These are our EOMs, equations of motion. Now I'm just going to spend some time talking through the green procedure of analysis. Okay, this is on page 120 in the textbook. This is how we're going to solve problems. Most of our problems are going to start with forces or moments given to us, and we're going to have to analyze the geometry and so. This is going to give us a kind of a checklist of what to do. First thing is select your coordinate system, your inertial coordinate system. Okay, in this case, or most often, we're going to be talking about rectangular. I'm going to do some example problems, and then we'll move on to tangential and normal components. Once you draw your coordinates, we're going to do a free body diagram, just like in statics. So far, this is pretty much the same. We want to account for all forces, and I do this the way my dynamics teacher taught me, was anything touching it could be a force that we need to consider, and is gravity in the picture? So do we have some mass times gravity term? Of course, there's other forces out there, but we're not concerned with them in this class. We're not even going to look at electromagnetic forces unless they tell us, hey, the force is a function of position. We're not going to not going to know where they came from without studying electricity and magnetism itself. Okay, identify all your unknowns. And you do this by figuring out what givens you have and then what you need to find. It's usually stated directly in the problem. And then from the free body diagram, make your equations of motion. This is your summation of the forces in the x, y, and z is equal to the mass times the acceleration in the x, y, and z. You're probably going to have to use some geometry. If in 3 dimensions, Cartesian vector analysis typically works well. You'll see a lot of problems will be just presented in 2 dimensions and can be solved as scalars. Then we need to look at what kind of forces may be acting, and it doesn't introduce this force except for in this little section right here. If we have a force moving on a rough surface, we might need to account for the friction. So let's just put a mass on a surface and maybe it's moving along with some velocity. In that case, if it's moving to the right, friction is always opposing the direction of motion. And we can calculate it. The force due to friction is equal to the coefficient of friction times the normal force. And we'll practice how to get that. In this case, we're on a flat surface, so if I drew a dot for the particle m, the first thing I would do is draw the mass times acceleration due to gravity down and a normal force up. Since it's on a flat surface, we can sum the forces in the y direction, say that's equal to mass times acceleration in the y. It's not leaving the surface in this case, so the acceleration is 0, and when we sum the forces, I get a positive normal force and a negative mg, meaning that they are equal. But okay, now we would take this and multiply it by mu, or the coefficient of friction. And if this was at some angle, we would have to introduce that angle to it, and I'll show you how to do that too. So if that's at some angle, we need to consider the mass hanging down and break it up into components perpendicular and parallel to the plane. So if you got a force of friction, we deal with it like so. What else do we got? We have spring forces. Alright, if the particle is connected to an elastic spring having negligible mass, which most will, the spring force can be used. And this is called Hooke's law, where the spring force is equal to Ks, and it's usually got a negative in front of it, meaning it works in the opposite direction of displacement. So if this dashed line is our equilibrium point, and there's my spring. If I pulled that out some delta S to here, the force itself, even though I pulled it to the right, the force itself is going to act back to the left. So that's where the minus sign comes from. It acts in the opposite direction of the displacement. If the particle was right here and the spring was being compressed, the force would once again act in the opposite direction, to the right in this time. Okay, once we have our forces analyzed, we can start looking at kinematics. This is what we studied all in chapter 12. That's why I said this was important stuff. Don't forget it. If we need to find the velocity or position of a particle, we can use kinematic equations once we have summed the forces and set them equal to mass times acceleration, or once Newton's second law is used. So we got to find the acceleration, right? Typically, it might be backwards. We might have to find the force, but we're typically given forces and have to find the accelerations or velocities. If acceleration is a function of time, then we would use things like the definition and then integrate it, and b is equal to ds dt, and integrate it to get new position or velocity functions respectively, or velocity and position functions respectively. If we have acceleration as a function of position, then we're going to use a ds is equal to v dv, which is eliminating dt from both of those. And then we would integrate it to find our new equations. If we have a constant acceleration, we can use our constant accel equations. And those are your v is equal to v naught plus acceleration times time. Your position is equal to s naught plus v naught times time plus 1/2 times acceleration times time squared. These have to be constant accelerations, and then we have v squared is equal to v naught squared plus 2a delta s. That's also got to be constant. Okay, there may be cases where we have to relate the motion of two particles. And this would be maybe like a Pauli problem or something, right? They have absolute dependent motion. So that would be something that we studied, I think it was 12.9, 12.10, 12.9. Alright, I think that wraps up the green box I wanted to talk through from 13.4. Go ahead and check it out though.